All right, ladies and gentlemen, this class recording has started. So, yesterday, we started off in this presentation here, and the title of it was, how do we get charges to do what we want them to do? So yesterday I had you guys start off with a couple of terms, right, reminding ourselves of some things, and we referenced those things, right, especially energy, our energy, the ability to do stuff. And this section deals with energy, but a different kind of energy. And we started off talking about electric potential energy. Because the fact that we call it potential energy, that means what? What does it deal with? It deals with position, right? It deals with where something is. Specifically, where something is within an electric field. We talked about that it's a form of mechanical energy, and if we move that object around, changing its position, we change its potential energy. And we talked about this page, right, where we looked at moving this charge around within the electric field, and how can we increase potential energy, how can we decrease potential energy, how can we not change potential energy, etc., etc. And then that led us to this picture, where we talked about these two different fields, right? One on the left, other than the fact that it's labeled strong electric field, versus the one on the right that is labeled weak electric field. We can tell the strength of the field by the number of arrows, right? And the one on the left is a stronger field than the one on the right. And we said that if we moved either of these charges within their respective fields, the one on the left would gain more potential energy because it's a stronger field. And we talked about the similarities between, like, dropping an object here on Earth versus dropping an object on the moon, right? And the amount of damage it can do because of the gravitational field. Same idea. And I believe that led us to voltage, right? This is where we left off yesterday. Right? So, when we talk about the voltage of something, we are referencing its ability to change energy. And that's also why we refer to voltage as potential difference. So, the potential difference tells the ability of an electric field to change the electric potential energy of a positively charged particle, or the difference in energy when we move it from one place to another. Okay? That's what the voltage tells us. It tells us about energy, and specifically about changing energy. Okay? Good so far? All right. Did we get these things? The definitions of what a volt is and stuff like that? Okay. So, let's go here. All right. This picture you guys have in your notes, okay? But not as much detail. There's some things I want to change. There's some things I want to add that will hopefully make it a little more clear, okay? So this is a picture, like it says up in the top left, of a closed circuit. It's a pretty simple circuit. And we'll talk about circuits a little bit more tomorrow. But first, it starts down at the bottom with a battery. And you'll notice that my battery up on the screen has some detail that your battery doesn't, right? What have I added to my battery? Arrows. What did we say that those arrows represented for us? Electric field, right? There is an electric field inside of the battery. It is the result of a chemical reaction that is occurring inside of that battery that creates an electric field. You will not be responsible for that chemical reaction or how it happens. That's electrochemistry. We're not there yet, okay? But just know that there is an electric field inside of that battery. Meaning that if we move charges within that electric field, we can either increase or decrease their energy, depending on how we move them. So, this battery is labeled as source of electricity. That's too general for us, right? Cross out electricity. Electric fields are actually sources of what? Electrical potential energy. Or we could say it is a source of voltage or a source of potential difference. All of those things relate to energy. Okay? Batteries do not add anything to the circuit that isn't there already. The only thing batteries do will increase the energy of stuff that is already there, namely electrons. Right? We said electrons are really the things that are easier for us to move around. So, in order for us to increase the energy of an electron, how would we move it within this battery? Well, there's two sides to that battery, right? There's a positive side and a negative side. How would we move electrons to increase their energy? Right. A negative electron wants to go where? So we want to put it in a place that it doesn't like, right? So it should move which way? It should move. Yeah, let's talk about electrons, okay? So, electrons move within the field in the battery. Sorry, I'll move this out of the way. In order to gain electrical potential energy. All right, everybody. If you thought yesterday's animation was good, just do weights, all right? So, I mean, wait, Marito. I'm just telling you this. All right, here we go. Ready? Oh, hold on.
Whoa, there's no sound.
No, sorry, no sound today. So, all right, so electrons move through the battery, and they move towards that negative side. Okay? We do work on the battery within the field and increase the energy. Just like me picking up the ball, raising it here, right? This is me doing work in increasing gravitational potential energy. That's the battery doing work in increasing electrical potential energy. Kenny, go ahead.
So how do we move it over?
Okay. That's what the chemical reaction inside the battery does, right? Basically, it just moves those electrons from the low potential energy to the high potential energy side, okay? But, do they like being there? No. And they will take that opportunity to move out of that position as quickly as they can. Just like this, right? This is an area of high gravitational potential energy. But if we let it go, what happens? It drops. What happens to its energy? What kind of energy increases? Kinetic increases as potential decreases. So what do you think happens here?
Whoa.
Right? So these electrons start moving within this path. The movement increases kinetic energy, but at the same time, the electrons are moving away from the negative terminal of the battery, so their potential energy is decreasing. Save that question for a second. All right, good there. Now, just wait, because this is about to get complex. All right, so we got this stuff written down here. If you want to, it's up to you. You don't have to write anything now. Okay? Yeah, test time. As long as you know it when the test comes around, I don't care what you do. All right, ready for the next? Okay. Prepare yourself. Ready? Here we go.
Oh, we could have sound effect on it.
Direction change. Whoa. So, other things that we put within the circuit have the ability to turn that electrical potential energy into other forms of energy, not just kinetic. So here, right, the light bulb turns the electrical potential energy into light and heat.
Okay, so if it goes into kinetic energy when you use the wire.
Yep.
But then where does it turn into electric potential?
Hold on. So the whole time, right, the whole time, Julian, what's happening to the electrical potential energy? It's being decreased because as it moves through here, right, it's moving farther away from this, but closer to this, right? So the electric potential energy is decreasing, but other forms of energy are increasing. Why? Because what do we know about energy? It's conserved. So if we decrease one form of energy, we have to increase another form of energy. That's what's happening here. Electrical potential is decreasing, but kinetic is increasing because it's moving. But now we've turned some of it into light and heat, so we can read and do whatever we want to. Okay, right? But hold on. To ultimately answer your question, we have to do one more step. Okay, Alex, go ahead.
So when it's in the battery,
Yep.
like after it's moved, so it's closer to the other negative.
Yep.
Why doesn't it just go back to where it was before?
Because the battery, the chemical reaction inside the battery, it's like a one-way street. It's like I'm forcing you this way because that's what the battery does. It increases the potential energy.
Just goes like out of the battery.
Right. Because if the battery continues to shuffle a bunch of electrons to this point right here, do they like being there? So they're going to look for any way out that they can, and that means they go this way. Does that make sense? Because the battery won't let them go back the other way. Does that work? Okay. All right. Eventually, right? Another direction change, right? Eventually it ends up back here, right? By the time it gets back to the positive side of the battery, it will not have any electrical potential energy anymore because positives and negatives like to be together. That is a low energy state. If we go back to our analogy with this, right? Actually, hold on. We'll hold on to that. So the battery gains energy, the battery causes the electrons to gain energy, and then as it goes through the circuit, it turns that potential energy into other forms of energy, ultimately ending back up with, could be heat, could be light, could be movement, just with kinetic energy. Depending on what we connect it to, could turn into like sound, or if it's like a buzzer or a speaker or something like that, right?
Like stuff needs like a computer battery gets hot.
Sure, yeah. Usually there's some heat, although the battery getting hot is more a function of the chemical reaction as opposed to those electrons moving. Okay? So, when we talk about the voltage of a battery, we talk about the difference in the energy that the electrons have coming out versus when they get back to the other side. So the voltage or the potential difference of a battery relates to the difference in energy. How different is the energy coming out of the battery versus when it gets back to the other side? All right, good with that? going back to our analogy of the gravitational field, okay? Technically, I could use the yellow ball, or let's say maybe like a bowling ball, right, to do something. Like, let's say I have to pound a stake into the ground, okay? Maybe not the most efficient way to do it, but I could just drop a bowling ball onto the stake until it falls, until it like drives into the ground. Maybe not the most efficient, but it could happen, right? So, but in order for me first to give the bowling ball the ability to drive the stake into the ground, what do I have to do? I have to pick it up, right? I have to do work on it. That's the same thing as what? That's the battery, right? The battery picks it up. And then we let it go, right? And we turn that potential energy into kinetic energy. The kinetic energy drives the stake into the ground a little bit. But we're not done yet. So what do you have to do? Pick it up again. That's the electrons going back through the battery. Then drop. Right? Pick it up again. Drop. Right? That's what the battery continues to do the entire time. Kenny, go ahead.
Are you using like the same electrons or?
Yes. A battery, that's good. A battery does not add electrons to a circuit or to a situation. The battery just increases the energy of the electrons that are already there.
So it's still moving through the battery?
Right, yeah. And Kenny, it could be the electrons that start off in the battery, but it could also be the electrons that start off in the wire. There's a bunch of electrons in the wire already. Right? So that's why here, where it says source of electricity, I don't like that because it's not really providing electrons.
Yeah.
All it's doing is changing the energy of the electrons that are already there. Go ahead, Alex.
Wait, so how do batteries die? Is that just because they lost the
Yep. If we go back to me picking up the bowling ball to drive the stake into the ground, right? Eventually I'm going to get tired and I'm going to stop doing it. That's the battery running out of the chemical reaction, right, that caused it to happen. Now, if we talk about a rechargeable battery, right, that would be like me getting tired so I can't lift up the bowling ball anymore, but then I sleep or go eat lunch or get a drink or whatever it is, right? And now I've got, I've recharged myself so I can continue doing the work on the bowling ball, or the battery is recharged so it can continue to do work on the electrons to continue doing their thing, right?
You know how you say when you hold the bowling ball in the air, it has potential energy? What is it when it just sits on the ground?
Does it have potential energy?
No.
No. Technically, it doesn't have any energy because it doesn't have any ability to do anything right now, right? We have to do work on it to give it energy so that it can then do other things. Okay? Technically, yeah, we're doing work instead of we're like that one. Audrey said if we kick it, that's doing work, right? Yeah, it is, but in that case, that work is going directly to kinetic energy. Whereas here, we're kind of going an intermediate of we're increasing potential energy, but then increasing kinetic energy because of that.
But
You get
the bowling ball have to move individually so if you take the bowling ball and then bowling it, like that should
correct. Technically, no, right? So if I kick the bowling ball and make it move, that would be work, right? Just like if I gave the bowling ball to a 2-year-old kid and said, "Here, pick this up," right? If they can't pick it up off the ground, they're not doing work on it either. That's a battery that doesn't have the ability to move the electrons enough to get them to do what we need them to do, right? That's like, putting this battery into your car, right? It just doesn't have, it can't do what it needs, it can't do the work that it needs to do to accomplish the other tasks. It's really good.
So, say you put the battery in the wrong way, and now there's
Yep. Yep.
Why is that?
Certain things within the circuit rely on the electrons flowing in a specific direction. And this gets into an electronics course a little bit, but there are certain things you can put in the circuit that regulate the flow of electrons that only let them go one way. Okay? The battery is one of them, but there are other things you can put in. So if you put it in backwards, right, the electrons won't flow in the right way because it may damage the components that are in it or something like that. Does that make sense?
Yeah.
So, now certain circuits it really doesn't matter. Like this circuit that's up here on the board, we could connect this battery either way and it would still do the same thing. Light bulbs are not one of those things that are one-way streets, right? You know, it would do the same thing, doesn't matter which way the electrons flow, but there are certain components that require that electrons flow in one way and one way only, and that's why we have the batteries in a certain way. Okay. Go ahead, Audrey.
Why do you need a switch?
You don't necessarily, unless you want to control when the electrons flow and when they don't, right? So if we just had wires, that would be fine. But if we're not in the room, right, and we don't want this battery using up its chemical reaction to increase electrons, potential energy to turn it into light when we're not in the room, we open the switch, and that does start the chain reaction. The first thing it does is it stops or breaks the electric field. Currently, I only have the electric field drawn in the battery, but really the electric field exists all the way through this, and that's how the charges move. It breaks the electric field. If it breaks the electric field, there's no force. If there's no force, there's no movement. If there's no movement, it doesn't do what it's supposed to do. Okay? So good.
Okay, and batteries are really bad and all that produce
Yeah.
and then dry load or whatever.
Yeah.
What is that?
That's just the stuff that was inside the battery that was making the chemical reaction. The casing, the case on it has just leaked, and it started reacting with other stuff inside, like the little metal parts on the whatever you put it in. It's just that reacting with the other stuff. So that's what it is. It doesn't do the same reaction as inside the battery, and that's why it doesn't work. Because reacting with the metal that's outside of it isn't the same as reacting with the stuff that's inside of it to produce the electric field. All right, good there? Okay, so why all these different batteries? First, before we do that, we have to introduce this term, current. Okay? So, current, the rate at which electric charges pass through a certain area of a conductor. The rate at which electric charges pass through a certain area of a conductor. If we're talking about electric charges passing through something, they need to be doing what? Moving, right? This gets into the kinetic energy part of that transfer of energy, right? It would be more, how often do I drop it? Right, yep, that would be more, yeah. Like me picking the bowling ball once every 10 seconds is a low current, but me picking it up once every 2 seconds would be a high current, right? It happens more often. All right, we got this? Good. Current is the movement of charge carriers, but usually we're talking about electrons, especially when we're talking about metals and conductors. Technically, current is the movement of any charge carrier. Could be positive or could be negative. Usually, though, we talk about electrons because valence electrons are a lot easier to move. In order for currents to occur, there needs to be an electric field, because that electric field causes an electric force. Remember, going back to Faraday, action at a distance, blah, 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 right? If there is no electric field, there is no current. And Audrey, that's what opening the switch does. It basically breaks the electric field, and so now the charges don't move and the energy doesn't change. Right. Or if instead of letting it fall all the way to the ground, like it lands on, the table or something like that, right? We stop the electric field, or in that case, we stop the gravitational field from doing what it does. All right, good there? Okay. Current. We use the letter I to represent current, okay? Current is defined as Q over T. Q we came across before, okay? The little triangles are delta. You can include those, so you don't necessarily have to, okay? Q we came across before when we were talking about Coulomb's law. Remember, Q represents charge. So Q over T represents charge over time. Say again? Triangle, remember, is delta. It's a Greek letter delta. It represents change. So we're talking about the change in the charge, how many charges go through, and the time during which it takes. If you just write Q over T, that'll be enough. So no, not right now. Much. Some simple ones. Okay, so the SI unit for charge is the ampere. Okay? We use the capital letter A. Usually, though, ampere gets abbreviated to amps. So when we talk about a certain number of amps, that's talking about how much charge is flowing through whatever we're talking about. Okay? Good there. So at the bottom where it says, or on the back of the next page, right? Or top of the next page, letter F, it says 1 ampere is the movement of. So, here at the top right, 1 ampere is 1 coulomb, 1 second. 1 coulomb over 1 second. Coulomb, we said, is our unit for measuring what? Coulomb measures charge, and then second measures time, right? So charge over time, just like the definition, okay? So a ampere, 1 ampere, is the movement of 1 coulomb of charge in 1 second. 1 coulomb, right, coulombs per second. All right, good there? Okay. Let's write these down real quick. Okay. So there are 2 kinds of current, and we'll talk more about these kinds of current later on when we start talking about magnetism. So, direct current, electrons flow in one direction only. Told you. This is the kind of current that we generally get out of batteries. There are some kind of generators that provide this kind of current, but mostly batteries. A potential difference, a battery, increases the electrical potential energy, which then we convert into other forms, which includes kinetic, and that's why it's current. Like I said, we will talk more in detail about DC and AC when we talk about, in the next part of this unit, when we talk about magnetism and electromagnetic induction. Doesn't that sound fancy? Yes, AC. I don't really like AC/DC. No. All their songs basically sound exactly the same to me. Yeah. Even Back in Black, I'm kind of like, you know. So. Actually, Hell's Bells is probably my favorite AC/DC song. So. What? If you're gonna make fun of me, I don't care. That's fine. I just don't like AC/DC. I just don't.
Every AC/DC song sounds good.
Exactly what I just said. If Kenny agrees, then it's obviously got to be true.
Yep. Well, I probably wasn't listening.
So, all right. For alternating current, we have electrons flowing in 2 directions. That can be a little misleading. It's not like certain electrons are flowing this way and certain electrons are flowing that way. It's actually sort of a back and forth, sort of jiggling. Okay? That each electron sort of goes back, forth, back, forth, back, forth, back, forth, back, forth. And how often it does that depends on the frequency. Like I said, we'll talk much more about this when we talk about electromagnetic induction and electric generators. It's easier to create electricity that way. So you can, there's a reason, and we'll talk about it why. All right, good there. Let's wrap up these 4 pictures that show up on the bottom of that page. Because, yeah, most of these things all work on alternating current. Anything that plugs into the wall is alternating current. So, you know, Alternating current and direct current basically can do the same things. It's just a matter of how we create them that makes them different. So, but ultimately they do basically the same things.
So one's stronger,
Not necessarily, but then either of them can be very, very strong. It just depends on how we create them and stuff like that. So, all right, current and voltage. Current versus voltage. These are two words that we kind of get confused and a lot of people aren't clear on. So let's make sure we clear it up, right? First, earlier I told you voltage sort of relates to what? The potential difference, or more generally, voltage relates to the energy, right? Or electric potential energy. So the ability of the charges to do stuff. But we just learned that current is more of a counting thing. How many charges are there? So if we have low voltage, what does that mean about the energy of each charge? It's not a whole lot. And if there's low current, how many charges are there? Not very many. So we have each electron carrying a little bit of energy and not that many electrons. Overall, we're not doing a whole lot of damage. All right? So, right? Each electron carries a little or low energy, or a low amount of energy, right? And there are only a few amount of electrons, or a small amount of electrons, right? And that means that overall, not a whole lot of damage, not a whole lot of energy, right? That's this AAA battery. 1.5 volts means, in the grand scheme of things, when electrons pass through this battery, they don't gain a whole lot of energy. But because it's so small, right? Not a lot of electrons pass through it. So overall, not a lot of ability to do damage with this battery, right? You can work a laser pointer or whatever else you might put it into. What? Well, that's a different kind of energy, right?
That's what I said.
It's a different kind of energy. All right. High current, low voltage. The fact that it's low voltage means what? Not a lot of electrical potential energy for each charge. But if there's high current, there's a lot of charges. Right? That's this battery. Right? It's only 1.5 volts, but how big is it? Pretty big. Meaning that it doesn't really charge up the batteries or the electrons all that much, but there are a lot of electrons coming out of it. Okay? Angela, go ahead. Okay, so voltage we said, right? Voltage is an energy. So the fact that this is low voltage means each electron carries a low amount of energy. Okay? Yeah, we're on the second picture now. Okay? And then, but there is a large amount of electrons flowing, or a high amount of electrons flowing. That's the current part. Right? And so, if you put low energy with a lot of electrons, you get a medium amount of energy. Okay? On the other side of that teeter-totter, right? High voltage, low current. The fact that it's high voltage means what? A lot of potential energy. But low current means not as many carrying charges, right? 9-volt battery. 9 volts. Each time an electron goes through this battery, it gains 6 times as much energy as this battery. 9 volts versus 1.5 volts. Not necessarily. Because, well, now it depends on what you say. Equal, right? This one, because it's small, doesn't let as many electrons flow through it. So, yes, there's less charges, but it might be able to deliver just as much energy, right? just not, or it might not have, it won't have as many electrons to do it. Now that doesn't necessarily mean you can replace this battery with this battery, okay? That because certain things require less current but more voltage, you know, to work or whatever it might be, okay? But overall, you might get the same amount of energy. Then we start getting into, right, the dangerous stuff. High current, high voltage, right? Now, we can have high voltage, right, which may not necessarily be dangerous. Okay? So, high current, high voltage, lots of energy, lots of charges. Anybody, I'm assuming you probably have before, anybody ever see a car battery before? So a car battery is about yay big, right? Okay? But a car battery is a 12-volt battery. So it's much higher voltage than any of these batteries, and it charges up a lot more electrons. That's why if you ever seen somebody try to jump a car, right? If you ever seen somebody try to do jumper cables, if you like put the jumper cables together, right, you get a big spark, right? Well, you shouldn't do that. So, unless you're Iron Man, I suppose. Then. All right, tomorrow we'll talk about circuits.
We're in the lab tomorrow, right?
Nope, Friday.
Friday.
What's your plans like? You look for balls, science on the ground.